Welcome to The Explainer. Today, we're tackling a massive, honestly super frustrating roadblock in modern AI engineering, the memory crisis. We're going to figure out how to solve the headache of stateless LLMs by engineering an Evermem-style, totally persistent AI agent operating system. So let's jump right in.
So, why does your AI forget literally everything you tell it? You know the pain. The core crisis we face as developers right now is that large language models are, by default, inherently stateless. Think about your standard chat interface. You might spend a solid hour giving the AI context, establishing ground rules, working through a really complex problem. But the absolute second that session ends or the context window maxes out, boom, the model wipes its slate completely clean. It retains zero knowledge of what just happened. You're basically hitting a factory reset button every single time you close your terminal. And if we want to build truly autonomous systems, we absolutely have to move past this stateless paradigm.
To fix this, we first need to define our end goal, which is agentic AI. The research defines this as systems that are capable of acting autonomously, adapting in real time, and solving really complex, multi-step problems based on context and overarching objectives. This is a massive leap beyond your standard generative chatbot. An agentic system manages tool execution, like running Python scripts or firing off API calls. It persists state across multiple sessions, and it orchestrates long-term goals with barely any human supervision. But of course, none of this autonomy is even possible if the agent can't remember what it did 5 minutes ago, let alone yesterday.
It's wild to look at the stark contrast between what most people are building right now and what we actually need to be building. On one hand, you have stateless generative AI. It's totally reactive. It forgets its context immediately, and its main job is really just churning out content based on whatever immediate prompt you feed it. But then you have the stateful Agent OS. This is proactive. It actually persists state, meaning it remembers your past interactions, it engages in continuous reinforced learning through experience, and it is relentlessly goal-oriented. And Agent OS doesn't just sit there waiting for a prompt, it observes its environment, it remembers where it failed before, and it actively plans its next move.
All right, so how do we actually engineer this stateful Agent OS? Well, it requires a fundamental shift in how we architect the whole system. We have to stop treating an LLM as this standalone, all-knowing brain and start treating it as just the reasoning engine within a much larger cognitive architecture. Because just like human cognition, an agent's brain is complex. To achieve real persistence, we have to look closely at the architectural breakdown of how memory is structured in advanced systems.
If you dig into the research, you'll see there are 7 distinct types of agent memory. We've got working, semantic, episodic, procedural, retrieval, parametric, and prospective memory. Each one serves a highly specific function, from storing hard facts to recalling past events, all the way to planning future actions. Now, while it's fascinating that there are 7 types, trying to implement every single one of them at once is just a recipe for a bloated, failing system. So instead, we're going to focus on building a very specific hierarchical stack that makes an Evermem-style OS actually possible.
So let's bring this down to earth. I want to walk you through the literal data flow of this hierarchical memory stack. This is how information moves from just a fleeting thought into permanent storage. Step 1 is working memory. This is your LLM's active context window, the tokens it's crunching right this second. Step 2 is episodic logs. Think of this as the exact sequence of events, your chat history, the tool actions taken, all stored sequentially. And step 3 is semantic vector retrieval. This is where the magic really happens. It's the long-term knowledge base where concepts and facts are stored based on their underlying meaning, which lets the agent recall relevant info across totally different sessions.
And the best part? You don't need some wildly expensive, proprietary black box to pull this off. We can map these memory functions directly to a rock-solid open-source tech stack. For semantic search, we use FAISS. It gives us blazing fast sublinear time retrieval for our dense vector embeddings. That's our long-term conceptual memory. For episodic logs, we use something as battle-tested and straightforward as SQLite. It handles the relational event logging so the agent knows exactly what happened and when. And for working memory, we just use the LLM's active context window. This specific combo lets the agent seamlessly pull historical context from SQLite and conceptual knowledge from FAISS right into its active working memory.
Now, I know what you might be thinking. Why go through all the hassle of building an external database? Why not just rely on the LLM itself? Well, it all comes down to parametric versus non-parametric memory. Parametric memory is the knowledge permanently baked into the neural network's internal weights during its initial training. The problem? It's completely static. Relying solely on that baked-in parametric memory is exactly what causes hallucinations, because the model literally cannot update its facts. And that is exactly why our Agent OS needs non-parametric memory. This is a live external corpus of data accessed via retrieval, our PhasEye and SQLite databases. It lets the agent pull verified, totally up-to-date facts without us ever having to retrain the underlying model.
Okay, let's roll up our sleeves and look at the pipeline. How do we actually cement that short-term working memory into our non-parametric vector database? We call this the automated consolidation process. First, the system ingests the raw session dialog. Second, because models have token limits, we chunk the text up using something like a character text splitter, say chunks of 500 characters with a 100-character overlap, just to keep the context intact. Third, we pass those chunks through a model like Hugging Face's All-Mini-LM to generate dense vector embeddings. Fourth, those vectors get stored and indexed directly in Face. And finally, step 5, when the agent faces a new query, it dynamically retrieves those stored vectors based on semantic similarity.
But wait, before you go shoving every piece of data into your model, we need to talk about a massive trap: context pollution. Lately, with the rise of models boasting 1 or 2 million token context windows, it is so tempting to just dump everything in there. Every log, every file, every past conversation. But research shows this is a terrible idea. Jamming massive schemas, full file trees, and endless chat history into the working memory completely pollutes the context. It actively degrades the model's reasoning, slows down your response times, and man, it absolutely skyrockets your API costs.
There's a quote from our research sources that really hits the nail on the head here. The solution isn't bigger windows, it's better curation. Context engineering means finding the minimum set of high-signal tokens. This is exactly why a hybrid search and precise retrieval system is an absolute must. Context is a scarce resource, especially when you're building terminal-native CLI agents that need to operate autonomously. You don't want your agent reading the entire internet every time it takes an action. You want it using its SQLite and FICE memory stack to retrieve just-in-time, highly relevant data to solve the exact problem right in front of it. And if you ignore this, if you just rely purely on a stateless LLM to make decisions, you are going to run into a wall of inaccuracies. Check out this number, 35%. The research reveals that agents operating without persistent memory or live web data suffer a 35% higher hallucination rate on tasks that require current information. 35%. In a production environment, an agent making autonomous decisions with a 35% error rate isn't an asset, it's a massive liability. Persistent memory is what actually grounds the model in reality.
But if you get this right, the return on investment is absolutely staggering. Look at this data from Anthropic tracking enterprise engineering teams. Teams that transitioned from basic coding copilots to stateful agentic tools ship their software 30% faster. But the real mind-blowing metric here is that they saved over 500,000 engineering hours across the organization. By giving agents persistent memory and the ability to autonomously orchestrate tasks, human engineers were completely freed from repetitive drudgery. They could finally shift their roles toward actual strategic decision-making and high-level supervision. That is a real game changer.
So, I'm going to leave you with the ultimate question for anyone building in this space. When your session ends today, what will your agent remember tomorrow? If your answer is nothing, then honestly, you aren't building an autonomous system. You're just building a very fancy stateless wrapper. It's time to step up. By implementing a hierarchical memory stack, combining the active working memory of an LLM with the episodic logs of SQLite and the semantic vector retrieval of Face, you can engineer a true persistent AI agent OS. Thank you so much for hanging out with me on this explainer. Keep learning, keep building, and I will see you next time.